Today we are discussing about the topic of threads in operating system. We have seen in the topics are under the understanding multi-threading types and implementation. Introduction to threads. A thread is a smallest unit of execution with a process. It allows multiple tasks to run simultaneously with a process. Threads share memory, data and resources of their parent process. They improve performance, resilience and resource utilization. Multi-threading enables running multi-threads at the same time. Used in modern application, gaming and multi-environments. Why are threads are important? Concurrency. Enable parallel execution of tasks. Efficient CPU utilization. Prevent CPU from being idle. Faster execution. Speed up process by overlapping tasks. Resources sharing. Threads share memory and variables efficiently. Responsiveness. Increase the performance in user applications. It increases the performance via the CPU utilization. That's why the response is increased. Multi-core processing. Take advantage of multiple core for efficiency. Process versus thread. Process. Independent execution unit with its own memory requires more resources and context switching. Inter-process communication, it's called IPC, is complex. Create using fork or system calls. Threads. Lightweightening execution unit within a process. Shares memory with other threads in the same process. Faster context switching than process. Created using threads libraries like POSIX, Python or Java threads. Types of threads. User level threads managed by user application, not OS. It's only threads are connected with the managed by user. It's not under the OS. Kernel level threads managed by OS require system calls. Single thread process. Only one thread executes at a time. Multi-threaded process. Multi-threads run concurrently. Hybrid threads. Combination of ULTS and KLTS for efficiency. Daemon threads. Background threads that run low priority tasks. Next, introduction to multi-threading models. Definition. Multi-threading models define how user threads are mapped to kernel threads is an operating system. Importance. Efficient thread management enhance CPU utilization, responsiveness and parallelism in applications. Types of multi-threading models. There are many types in the multi-threading. The first type is many-to-one model. Multi-user threads map to single kernel thread. Pros: efficient thread switching, less overhead. The disadvantage is no true parallel execution, blocking one thread blocks all. Next type is one-to-one model. Each user thread maps to separate kernel user thread. Advantage is true parallelism, better utilization on multi-core CPUs. Disadvantage is high overhead due to thread creation and management. Many-to-many model. Multi-user threads map multiple kernel threads. Advantage: balance efficiency and flexibility. Allows better scalability. Disadvantage is more complex to implement. The model is the first model is many-to-one. Advantage is lightweight and simple. Disadvantage: no parallel execution. Example usage: yearly Java threads. Next one is one-to-one. True parallelism, high resource usage, Windows, Linux, P threads. Next model is many-to-many. Advantage is balanced performance. Disadvantage is complex management. Example usage: modern OS scheduling. Multi-threading models. Many-to-one model. Multiple user threads made to one kernel thread. One-to-one model. Each user thread has corresponding kernel model threads. Many-to-many model. Multiple user threads may map to multiple kernel threads. Hybrid model combines many-to-one and one-to-one for better performance. Java's threading model follows the one-to-one model. Linux uses native POSIX threads for handling threads. Thread lifecycle. New thread is created but not yet started. Runnable, ready to run, waiting for CPU execution. Running, actively executing on CPU. Currently, the process is now running in the current user is called running. Blacked or waiting, paused, waiting for resources. The one task is performed, but it's waiting for the resource or response for continue the process. It is called blacked or waiting. Terminated. Threads has finished execution. Threads can be scheduled using FIFO, round robin or priority scheduling. Thread synchronization. Race conditions. When multiple threads access shared data simultaneously, critical sections, code segments where shared resources are modified. Mutex. Mutual exclusion. Allows only one thread to access a resource at a time. Semaphores. Used for managing multiple resource access. Monitor logs. The prevented simultaneous access to shared data. Deadlocks occurs when two or more threads wait identically for resources. Next one is advantage of threads. Faster execution, reduces process overhead and increase speed. Efficient resource sharing, use a shared memory instead of inter-process communication. Better responsiveness, improves user experience applications. Lower memory usage, threads within a process share the same address space. Utilize multi-core processor, executes task as parallel on different cores. Ideal for web server and database. It is handle the multiple user requests efficiently. Next, challenge in thread management. Context switching overhead. Switching between threads consume CPU cycles. Next one is deadlock and starvation. Threads may get stuck avoiding the resources. Synchronization issue. Managing shared resources requires locks. Debugging complexities. Multi-thread programs are harder to debug. Next one is thread priority issue. High priority threads may starve low priority threads. Next one is scalability constraints. Too many threads can overload the system. Thread scheduling algorithm before. It's called first in first out. Execute threads in order they arrive. Next one is round robin scheduling. Each threads get a time slice used in time sharing OS. Priority based scheduling. Threads with a higher priority execute first. Next priority one by one executed by this priority based scheduling. Shortest job next. Executes the thread with the shortest execution time first. The lowest time execution is run in firstly. Next one is multi-level queue scheduling. Groups threads based on priority levels. Thread pools pre-created threads improve performance in high load systems. Real world application of threads. In real world operating system handle multiple background tasks. Web browsers load multiple tabs simultaneously. Game development, render graphics, AI and basics separately. Data processing used in big data and machine learning for parallel computing. Banking and e-commerce handles concurrent transaction. Cloud computing, multi-threading is essential in distributed computing. Case study threading in Linux introduction. Threads are lightweight process that share memory and resources. Linux uses POSIX threads for multi-threading. Threads improve performance, responsiveness and CPU efficiency. Kernel-level threading allows direct OS management of threads. Thread management is done using the clone system called used in web browsers, database, gaming and AI application. Linux thread scheduling and synchronization. Completely fair scheduler CFS allocates CPU time fairly among threads. Real-time scheduling uses FIFO first in first out and round robin. Thread synchronization issue prevents race conditions and deadlocks. Mutes and semaphores used for thread locking and resource control. CPU affinity allows binding threads to specific core for better performance. Efficient multi-threading. Linux optimizes multi-core processor with threads pools. Real-world applications are Apache web server. Problem: Apache needed to handle thousands of client requests efficiently. Solution: used multi-threading worker MPM model for parallel request processing. Implementation: created a thread pool assigning new requests to existing threads. Optimization: used load balancing, caching and async I/O for fast response. Outcomes: improved speed, scalability, and efficiency in web hosting. Conclusion: thread help reduce server response time and handling heavy traffic. Challenges: Linux threading enables high performance computing and efficient multitasking. Used in browsers, database, AI, gaming, and cloud computing. Challenge: race condition, deadlock, and high memory usage. Thread synchronization is essential to prevent conflicts. Multithreading continues to drive innovation in computing. Conclusion: Linux threading enables efficient multitasking and high performance computing. The completely fair scheduler CFS and Pathod's library making threading efficient. Real-world applications include web servers, databases, browsers, and AI processing. Challenges like deadlock and race conditions can be measured with process synchronization. Multithreading continues to drive innovation in operating system and high performance computing. Thank you.